For many lean practitioners and CI leaders, there's one nut that's been hard to crack. It's not because the principle is not worthwhile, but rather because it always seems so complex. That principle is OEE, or Overall Equipment Effectiveness. As it is normally presented, with convoluted diagrams, it's easy to get frustrated and decide that it's just not worth the trouble to understand. But OEE is a powerful concept that you have probably used dozens of times and just didn't realize it. That magical number that you've been using to estimate how much capacity you've been losing to all the stuff that happens is nothing more than a rough estimate or a guess at OEE. So let's make it simple, and let's look at OEE in a nutshell. To illustrate OEE, we need a process to examine. Here we have a stamping machine. It presses out large stars from a red ball of plastic that is fed into the machine through the chute at the left. It rides the conveyor and stops just under the ram. After the ram compresses the ball into a star shape, the part continues its ride on the conveyor out of the machine and falls onto another conveyor, leading to the hardening operation. Sounds simple, right? What could go wrong? Well, actually, several different things can go wrong. And as most people know, especially when you have that hot order or that new customer you're trying to impress, the wide variety of issues that can arise have been classified into three categories. They are availability, performance, and quality. We'll look at each of these categories individually so that we can understand where that OEE number actually comes from. The first category of OEE to consider is availability. Just because a machine is sitting on the shop floor does not necessarily mean that it's available for production. In actuality, there are a ton of events and conditions that cause the machine to not be available when needed. In the best of all worlds, our machines would work correctly and consistently every second that we needed them to. But we do not operate in the best of all worlds. Failures and setup time often rob us of precious production. In the instance seen here, the red plastic ball is fed into the machine, and the internal conveyor carries it under the ram. But the shaft is stuck, causing the ball to exit the machine without being stamped. We call this a missed operation. This event or downtime loss is felt at least twice. We're hurt by the loss of manufacturing capacity, as well as the setup or maintenance work needed to resolve the issue. Of course, there is the issue that the red ball either moved on to the next operation or is sitting in a dunnage. Some of the areas of downtime loss to be considered are failures like the shaft getting stuck, setup or changeover time, cutting tool loss due to breakage, replacement or adjustment, startup loss. In most operations, there is some period of time between when the machine is technically runnable, but perhaps not making acceptable parts. Both the unacceptable parts produced and the lost capacity, as changes are being made, need to be considered. Time that the machine is not scheduled for production, such as unexpected meetings, fire drills, and such events, should also be taken into account for OEE. Though necessary, each has its effect on production. Availability, then, is a measure of the percentage of time the machine actually runs compared to the amount of time it's planned to run. The equation for calculating available time is running time divided by net operating time. For example, if the machine ran 300 minutes and it was planned to run 400 minutes, the machine's availability percentage would be 75%. Or we could say it has a 75% availability. What this means is that when we're planning production, we can only count on the machine running 75% of the time we actually planned on it running. This is a serious consideration. The next category to consider for OEE is performance. Whereas availability encompasses stoppages of the equipment or process, performance addresses those times when the machine might not be operating at its expected speed or timing. In this scenario, our plastic ball is fed into the machine and rides the internal conveyor to its position under the ram. But there is a delay in the action of the ram. This delay extends the repeated cycle time of the machine to be longer than the rated cycle time. This recurring delay can have a more drastic effect on production than a short stoppage because it is multiplied by the number of parts being produced. For example, extending a planned cycle time of 6 seconds for a part which we need 600 parts per hour, which is a 6-second planned cycle time, to 9 seconds would result in only achieving 400 pieces per hour as opposed to the 600 we needed. Thus, seemingly small repetitive delays can add up fast. But the good news is that small repetitive improvements in cycle time can also add up fast. As with availability, performance, also stated as a percentage, is simply a comparison or ratio of the actual output of the machine or process to the planned or target output. For example, if our machine was supposed to produce 20,000 parts during a given period of time, let's say a week, but in actuality it only produced 12,000, we would divide the actual by the target to arrive at a 60% performance rate. As you might guess, a low performance percentage would definitely be a matter for concern. It would be somewhat akin to running your car on only 5 of 8 cylinders. You would definitely want to find out and troubleshoot the source of your low performance. Our third OEE category is quality. We all know how costly low quality can be, what with the lost revenue due to scrap parts, as well as the challenging issues of sorting and rework. In this scenario, our plastic ball ends up under the ram, but it's not positioned right and is stamped into a defective shape. The customer is expecting a star shape, so it would not do to send him something that looks more like a deformed X. There's nothing to do but sort and throw away the defective parts and replace them with good ones. This situation hits us twice, first with the loss of the original product, and second with the capacity we had to use to replace the defective parts. So we pay twice for one mistake. And of course, Murphy's Law says that this will happen the most on those critical orders. Our final category, quality, is again a percentage that represents the number of good parts attained versus the total number processed. The calculation is good output divided by actual output. For example, if we processed 12,000 parts, and at the end of the process we ended up with 11,760 parts that we could sell to the customer without being reworked, we would divide the good by the actual output to arrive at a 98% quality level. You might note that defect losses include products that can be reworked as well as outright scrap. First pass quality is the goal. For production planning purposes then, this measure means that we should take into consideration our normal quality percentage when planning for how many pieces to start through the process. If we don't, we can end up with a short shipment to the customer. We've discussed the 3 categories of OEE individually. We've learned that each of the categories can be expressed as percentage or ratio that characterizes a machine or process in relationship to that individual category. But in actuality, we learn a great deal about why we can't seem to get what we need out of our machines or processes when we see how the 3 categories of availability, performance, and quality compound together to rob our capacity and throughput. Let's take a look at how it all stacks up. For our example, we have a machine that is rated to produce 100 pieces per hour. We needed 100 pieces to ship, so we originally counted on only having to run the machine for an hour. We see that represented by our stack of 100 parts that we expect to get from this hour's work. But the first problem we run into is that the machine has lately only been running 75% of the time due to frequent changeover and breakdown issues. This happens frequently enough that every hour of operation is affected. So in our planning, we can only really count on getting 75 pieces for an hour's work. Of course, that's if the machine is running at rate when it's functioning. That 75 pieces is represented as the next, somewhat smaller stack to the right. But our next challenge is that the machine is only running 60% of the rated speed when it does run. This is due to surface finish issues that were resolved by slowing down the speeds and feeds of the machine. So instead of being able to run at a rate of 100 pieces an hour for the equivalent of 3/4 of an hour, getting 75 pieces, we end up running at a rate of 60 pieces an hour for 3/4 of the time that we're able to run. This means we only ended up getting 45 pieces for an hour's worth of work or dedicated time. That's our even shorter stack to the right. And finally, of the 45 pieces an hour we ended up with, at a 98% quality rate, we had to throw one of the pieces away due to defect. That left us with 44. The OEE calculation associated with the scenario is pretty simple. It's expressed by multiplying our availability percentage times our performance percentage, then by our quality percentage. The result is an OEE, or overall equipment effectiveness, for us in this scenario of 44.1%. You'll notice that the two first components of OEE are time-based, while quality is output-based. What that means for us is that we will have to allocate a little over 2.5 hours of machine time to get the 100 good parts we really needed to ship. And we'll have to start at least 1 or 2 extra through the process to offset the quality loss. It's no wonder our scheduler and our production manager are fit to be tied, and we wonder why we can't seem to get out of the overtime routine. We've discussed overall equipment effectiveness in the 3 categories that contribute to it. We've learned that availability, performance, and quality percentages each affect how your machinery or process performs. Let's take a minute to discuss how we would use OEE and category percentages in our improvement efforts. First, let's assume we have a fairly complex process, such as you see here, that consists of several connected and disconnected workstations. We know that the line just hasn't been producing the throughput that the line was designed to achieve. We're getting further behind every day. The first step would be to gather data and to calculate OEE for each of the key workstations. We could then compare the OEE percentages to see if there appears to be a bottleneck operation. Looking at the OEE percentages shown here, which workstations might be of concern? You probably chose the aerator station to the left with its OEE of 58%, and the conveyor station to the right with its 68%. Let's take a look at the aerator station first, simply because it's the lower of the two. In our example, the data for the 58% OEE workstation shows that though it has decent performance and quality levels, its availability at 70% is where we need to work next. We next do some research and find that there are 2 issues with components of the machines that are worn and need replaced. We order the new parts, get them installed, and then track the results. As a result of this work, we find that our availability has gone up to 96%. How does that affect OEE? Recalculating, we see that our improvements have boosted the overall equipment effectiveness to 80%. The aerator workstation is no longer the bottleneck operation for the line due to the OEE percentage increase from 58 to 80%. Our next move would be to focus our attention on the conveyor system on the right with its 68% OEE. This process of focusing on the next challenging bottleneck operation as you make improvements is known as chasing the bottleneck. You might wonder why we would not stay at the aerator station until we got it as good as it could be, then move on to the next challenge. Remember that our goal is to improve OEE, which is now affected the most by the 68% conveyor system. It makes sense then to reassess after each incremental improvement and target the resulting low OEE performer. Another comment: that conveyor is at the head of the stream, so every operation would likely be affected by it. That's overall equipment effectiveness, or OEE, in a nutshell. We've learned how performance, availability, and quality are taken into consideration when expressing OEE for a given machine or process. We've also seen how OEE and its category percentages provide a ready way of knowing where to look and what to work on in our continuous improvement efforts.